Okay. In the last class, in the yesterday's class, we have discussed about the steady state stability, right? So we have gone through about the steady state stability in the previous class. That is how to determine the steady state stability. For the determination of steady state stability, we took one example as increasing the load, which it is a very small and gradual disturbance. So we have considered one condition as an increase in the load. So with respect to that increase in the load, how we are going to calculate the dp by d delta. Okay. So we are going to calculate the dp by d delta is dp, that is change in active power, divided by the change with respect to angle. I already told whenever a disturbance is going to take place, then there will be change in the rotor axis and there will be also change in the angle of delta. Just because of the change in the angle of delta, there will be also change in the power. So to determine the steady state stability, we need to find out what is this change in active power with respect to change in delta, that is dp by d delta. If this is a positive, if this is a negative, or if not, if this is a zero. We have three conditions of this tree, that is of this value. Either it may be a positive, negative, and zero. If it is a positive, we are going to call that system as a stable system. If it is a negative, then we are going to call that system as an unstable system. If it is a zero, then we are going to call the system as a critically stable system. So based on this method, based on this one, we are going to decide the steady state stability, either it is getting the stable or not. If we are getting the change in the active power with respect to change in delta is a positive value, that indicates that it will reach to the stability limit at any point. Okay, that's not a problem. Okay, that indicates it is going to operate under the steady state stability condition, right? But if it is a negative value, that indicates that it will never reach the stability limit, that is that operating point, that indicates it is an unstable condition. Okay, so it is critical stable, that indicates that there is no disturbance. You can assume that as it is not going to affect the stable. Okay, it is exactly the maximum power it could able to deliver. We are going to call it as a stable system, which we have already discussed. We already know that the active power, that is the power delivered, that is P, is directly proportional to sine delta. We already know that P is directly proportional to sine delta, that is this one. Therefore, you're going to draw the axis with respect to P versus delta as coming to the steady state stability. We have tried to determine about the steady state stability. So when we have determined that one, we got this equation, that is we got this as the roots. Okay, these are the roots. So that is P is equal to plus or minus dou P by dou delta at an initial angle delta naught divided by M. Okay, I already told this M is nothing but an angular momentum. That is, it is a quantity of rotating body. We are going to call it as an angular momentum. So we are going to get these values, that is we are going to get dp by delta as a positive when delta is less than 90 degrees and when the roots are pure imaginary and conjugate. So the dp by d delta is a negative when delta is greater than 90 degrees and when the roots are real. Okay, and dp by d delta is equal to 0 when delta is exactly equal to 90 degrees, and we are going to call this as a critical stable system. So that is the thing what we have discussed here, that is the change in the active power with respect to change in delta. Either it may be a positive value, negative value, and a zero value. If it is a positive, then we are going to tell that the synchronous machine is achieving its stable condition. If it is a negative value, then we can able to say that the synchronous machine is not going to achieve the stable condition, that is it is going to operate under unstable condition. Okay. If it is a zero, then we are going to call it is going to work under the critically stable condition, right? So if you see here, if I want to draw the characteristics of P versus delta, which we already know P is directly proportional to sine delta, this is the power delivered and this is the delta. So if you see, if this is an exactly the 90 degrees, okay, So we are going to call this as a stable condition if the change in power is less than this 90 degrees. If the change in power is greater than this 90 degrees, then we are going to call this as an unstable operation. I've already told the synchronous machine should be always operate under the stable condition or a critical stable condition. It should not move beyond this 90 degrees. If it is moving beyond this 90 degrees, it could not able to deliver the maximum power, but it will deliver the less amount of power. The power amount will decrease and it will run into an unstable operation. So we are going to take some necessary methods to improve this steady state stability. So what are those methods? So that actually depends on not this delta, but that is actually depending on this excitation voltage of a generator E and the terminal voltage of a load V divided by the reactance from the generator to the load inside X. Okay, that is, it is going to this maximum power. We need to deliver the maximum power. So that means it is directly proportional to E, directly proportional to the terminal voltage, directly proportional to the reactance. E is nothing but an excitation of a synchronous generator. V is the terminal voltage at the load end side. X is the transfer reactance from the sending into load end, nothing but an from generator side to the load end side. So what happened? Which it is a directly proportional. You can see if you are increasing this internal EMFs of the machines, okay, either excitation voltage or a terminal voltage of the motor and excitation voltage of a generator, if you are increasing that one, therefore the maximum power is going to get increased. That means we have one method is called as increasing internal. If you are increasing the internal EMFs, what happens? Obviously, internal EMFs means either that is a synchronous generator or that is a uh, terminal voltage of a synchronous motor. Okay, I'm assuming the load as a motor. If I'm assuming the load as a motor, then terminal voltage of a motor and excitation voltage of a generator. So if these are increasing, means automatically the maximum power delivered will also increase. So this is one method. So which it is possible by using the excitation system. We already know the synchronous machine is a double excited system. Next, how we can able to achieve the maximum power? It is possible to achieve by reducing the reactance. If you are reducing the reactance also, the maximum power could able to increase. So how you are going to reduce the reactance? We need to reduce. These all concepts which we have discussed in yesterday's class. Just I'm revising. We need to reduce the reactance. If we want to reduce the reactance, we have a few different methods. How we are going to reduce the reactance? So we can reduce the reactance by using a parallel transmission lines. Using a parallel transmission lines, what happens? The reactance, the equivalent reactance value will be get decreased. Okay, the equivalent reactance value will be get decreased. That is, X equivalent will be get decreased. If X is decreased, then automatically the maximum power delivered will also increase. So for this reason, we are going to use the parallel transmission lines. Coming to the second part, how we can able to reduce still the reactance? By using the bundled conductors. If you are using the bundled conductors, what happens? What is actually the bundled conductors configuration? So by using the bundled conductors, we know that the capacitance will increase. So by using bundled conductors, the capacitance will increase, whereas the inductance will decrease. We already know this one. So if the inductance is decreasing, means the reactance or the inductive reactance will also decrease. So that means the reactance we can able to decrease by decreasing using the bundled conductors. Therefore, the maximum power delivered will also increase. Okay. So this is one method. Next, coming to another method, we also have another method, last method, called as if you are using a series capacitors. For example, if I'm using a series capacitors, what happens? For a transmission line, if there is a transmission line like this with a value of X, okay, if there is a transmission line like this with value of X, then what I want to use, I'm going to use a capacitor in series with this one. So this value will be minus, have X1, this one will be X2. See, we will discuss about the slack bus that is actually related to the second one. I will clear your doubts in the last 10 minutes session. Okay, Rajanja. Okay. I will keep this point and I will clear. So if we have an x1 minus x2, so x1 is actually reactance. You have used the series capacitor. For that reason, the reactance, the total reactance now it will get decreased. The total reactance now you will get as x1 minus x2. That means the reactance is decreasing. So therefore you are going to increase the power transfer. So whenever you are increasing the power transfer means you are achieving the steady state stability. Okay, power transfer should increase so that you're going to achieve the steady state stability. So these are the two different methods. Again, in the second method, we have another three methods which it will be able to reduce the reactance. So these are the concepts what we have discussed about the determination of steady state stability, which depend on the dp by d delta, and also the methods to improve the steady state stability. Clear? So these are the concepts which we have discussed in the yesterday's session. Now let us try to understand about the transient stability. Okay. So now coming to a transient stability. What is actually transient stability is? So coming to transient stability is nothing but an. So it is an ability of a power system. It is the ability of a power system or a generator to maintain the synchronism even after sudden and large disturbance. Okay, even after the sudden and large disturbance. I have told you depending on the type of disturbance we have categorized the stabilities, right? If it is a slow and gradual disturbance, then we are going to call the disturbance as a steady state stability. If there is a sudden and large disturbance, then we are going to call this disturbance as a transient stability, right? So this sudden and large disturbances may be the bulk load or bulk removal of the load, or transmission line switchings, or transmission line switching means either you are removing a transmission line or either you are adding a transmission line to the power system network, or switching of a generators, or uh, the fault is going to take place on a transmission lines, especially the severe faults, nothing but three-phase faults. At that time, we are going, if the machine is achieving the stable condition, then we are going to call that stable as a transient stable. Okay. So if it is still achieving the stability condition, then we are going to call that stability as a transient stability. So let us discuss about transient stability. If you want to discuss about the transient stability, the first important point what we need to discuss about is nothing but a swing equation. I've already told in the last class that this is actually swing equation. So swing equation, we need to derive the swing equation. So after deriving the swing equation, we need to determine methods to determine the transient stability also we'll look over. So first, what is actually swing equation? I've already told what is a swing. Swing is, for example, if you have a stator axis and if you have a rotor axis, okay, if this is a stator and if this is a rotor axis, and the angle difference between this one, you can assume it as a delta. We already know. So delta, theoretically, I'm saying that it is a theoretical definition of a delta is it is the angle difference between the stator axis and the rotor axis, or we can also call it as angle difference between the excitation and the terminal voltage. Okay. So that is, if there is any disturbance is going to take place, what happens? If there is any disturbance is going to take place on a synchronous generator, this rotor axis maybe get accelerated or maybe get decelerated. So then whenever it is getting accelerated or decelerated, the only change which you can able to observe is nothing but delta. So everything is going to change after the delta is going to vary only. So here, if you see, the delta is going to vary. So for that reason, we need to, this change in the rotor axis is called as a swing. The change in the rotor axis is called as a swing. Okay, we are going to call it as a swing. It is a change in the rotor axis. Okay, then we are going to call it as a swing. Okay, so we need to find out the equation. If you want to find out this equation, is that is if the change in the rotor axis with respect to the function of a time, then I'm going to call this equation as a swing equation. Just I'm trying to define the swing equation. Okay, this is actually the change in the rotor axis as a function of a time. Call it as uh, the relative motion. You can also change in rotor axis. You can also call physically as, using a physical definition as, the relative motion of a rotor axis with respect to the stator axis as a function of a time is called as swing equation. That is, the change in the rotor axis, the relative motion of a rotor axis with respect to stator axis is nothing but d delta. As a function of a time is nothing but dt. Okay, d delta divided by dt, d delta divided by dt is nothing but will help us find out the swing equation. Okay, this is actually a swing. Swing equation means this is not exactly swing equation. We need to derive. Okay, so this is actually the definition of a swing equation. Okay? So the relative motion of a rotor axis with respect to the stator axis as a function of a time is called as a swing equation. Very, very important definition. He will mostly they are going to ask you this as your short answers. Okay. So the relative motion of a rotor axis with respect to the stator axis as a function of a time, okay, is called as a swing equation. So now we will try to discuss. We'll try to derive the swing equation. Okay. So we'll try to derive the swing equation here itself. So first, for example, I took one synchronous generator, and we will try to take one synchronous generator. Okay. So I took one synchronous generator. So for this synchronous generator, what I'm saying, so this is uh, the mechanical torque, or we are going to call it as also shaft torque. What is the input you are giving to the synchronous generator? Okay, we are going to call that as a shaft torque or mechanical torque. In some textbooks, you will going to call it as a mechanical torque. And what the synchronous generator is delivering is nothing but an electrical torque or electromagnetic torque or electrical torque. Okay, so TEM also you can write it. If not, you can also write it as a TE. Okay, that means I can able to write the accelerating torque, that is TA, accelerating torque. We are going to call it as an accelerating torque is nothing but an torque is nothing but it is a difference between the shaft torque minus electrical torque. Minus electrical torque. You already know that if you are considering the directions of the shaft torque and an electrical torque, you will get in an opposite direction. You can see this is actually shaft torque direction. Torque direction will be in opposite direction. In case of generators, I think you already have the knowledge. So shaft torque minus electrical torque will give you an accelerating torque. So obviously, for example, if there is no disturbance, what happens to this torque is it will be equal to 0, because the shafted torque, the amount of shafted torque is also equal to the amount of electrical torque. Therefore, it is equal to 0. That means neither it is going to accelerate nor it is going to decelerate. That is, it is going to work under the equilibrium condition. Okay, under the equilibrium condition. Okay, just I'm trying to say the one important thing is have an equilibrium condition means equilibrium condition indicates that there is no disturbance. You could not able to call it as a stable. Please understand the difference. You should not call it as a stable. Okay, you could not call it as a stable. Okay, if you think practically, you could not call it as a stable. It is operating under the equilibrium condition. When you're going to call it as a stable, you're going to call it as a stable if there is any disturbance is going to take place. If there is any disturbance is going to take place, and still if it is operating under the equilibrium, that is, if it is achieving to the equilibrium condition, then you're going to call it as a stable. If it is not achieving the equilibrium condition, then you're going to call it as an unstable. Clear? So anything you're going to call it as a stable or unstable depending on the disturbance only, depending on the type of a disturbance. If there is no disturbance, then it is continuously working as an equilibrium condition. But in the power systems, it is practically impossible, because in a power systems, usually there will be a disturbance. Always there will be so many number of disturbances. Okay? So now accelerating torque is equal to 0 if there is no disturbance, but practically it is not possible. Okay, so I could also write, if I want to write this accelerating, so if I want to write this accelerating torque in terms of a power, how I can able to write? You need to multiply with omega, right? I'm going to write EA into omega. What is this omega? Omega is nothing but an angular velocity, okay, which it is equal to 2 pi ns by 60, right? Where omega is nothing but an 2 pi ns by 60, which we already know. So we are going to call it as an accelerating power. right? So I can also write, see, I can also write this accelerating torque as, which it is the product of moment of inertia, which you are going to represent with I, into alpha into omega. I into alpha into omega. Okay, so we are going to call it as this product. We are going to call it as an accelerating torque, and which this torque is nothing but it is the product of the moment of inertia. I indicates the moment of inertia. This moment of inertia of the rotating body. Okay, we are going to call it as moment of inertia, right? But whereas this alpha, we are going to call it as an angular acceleration. Okay, okay. I indicates, but this alpha indicates the angular acceleration. Okay, this indicates actually the angular acceleration, or we are going to call it as an. What is this acceleration? We will discuss when we are discussing about when before completion of this derivation itself. Okay, so now I can write. I'm going to write the accelerating power is equal to I into alpha into omega. But we also have another definition. There is another thing. We are also trying to include the moment, angular momentum. Angular momentum means, how can I able to define? Angular momentum means there is m into alpha is nothing but an angular momentum. So m indicates an angular momentum. Okay, m indicates angular. So, so which is nothing but an m into alpha is nothing but an angular momentum. What is this angular momentum? Again, it's equal to angular momentum is equal to I into omega. If you see here, angular momentum is nothing but it is a quantity of rotating body. If you want to measure any quantity of a rotating body, then we are going to represent with an angular momentum, which it is a product of moment of inertia and angular velocity. Moment of inertia and angular velocity will give you angular momentum, right? So moment of inertia and angular velocity, that is omega. I into omega will give you, I will write also here, which is equal to I into the angular momentum, right? So therefore, this is actually the accelerating power. So we got an accelerating power which is equal to m into alpha. So m indicates an angular momentum, which is a quantity of a rotating body. Now let us try to understand the another concept here. So now I will try to draw the characteristic. Just I'm revising here whatever we have done. The accelerating torque is nothing but which it is the difference between the shaft torque and electrical torque, which it will be equal to 0 under the equilibrium condition only. I'm saying here, if there is no disturbance, okay, condition, or you can also call it as a steady state condition, no problem. This equilibrium condition or steady state condition. So if there is no disturbance, then accelerating torque will be equal to 0. So accelerating power we could also able to write as accelerating torque into omega. So accelerating torque also we can define as it is the product of the moment of inertia and acceleration. Angular acceleration will give you the accelerating torque, that is I into alpha. Moment of inertia I have indicated I, I have indicated with alpha, and omega is nothing but which it is already there. So I into omega, if I want to write in terms of angular momentum is, it is the product of moment of inertia and the angular velocity. So it will give you I into omega. So therefore you will write it as this, we are going to write it as m into alpha, because I into omega is m, so m into alpha. So this is actually the accelerating power. So we'll come to this point later. First of all, we'll try to discuss another important concept. So we'll try to discuss another important concept, that is, see here, usually I have already told there is a delta is a nothing but a difference between the stator axis and the rotor axis, but that is actually theoretical. But in practical, that is not exactly the right one. In practical, if this is, we are going to call this axis as a synchronously rotating axis, which it is represented with omega. Okay, this is actually omega r. Okay, so that is not WR, that is an omega r. Okay, right? Just I'll try to reduce the size. So this is actually an omega r. Omega r is a rotating speed. Either you can be able to indicate with NR, either you can be able to indicate with omega r. Okay, both will be same. And here, this is actually, we are going to call it as a synchronously rotating axis. This is actually synchronously rotating axis. This axis is a synchronously rotating axis. Okay, so this is, I'm not going to call it as a stator, calling it as a synchronously rotating axis. If you have a very thorough knowledge on the synchronous generators or synchronous machines, you will get this idea. You will have one axis called as this synchronously rotating axis. We also have another axis. We are going to call this axis as now the stator axis or a reference axis. Okay, this is actually another axis called as stator axis or reference axis. This is actually another axis. Now we also have other axis, nothing but an rotor axis. So this is, which this rotor axis is also going to run with speed. You can call it as a synchronous speed. Okay. So if you observe clearly here, we have a three axis. One is a stator axis or a reference axis. The other one is a synchronously rotating axis, which it will be always rotate with omega r, and we have a rotor axis, which it will be always rotate with omega s, synchronous. So if there is no disturbance, under the no disturbance condition, usually that omega r is nothing but an omega s. You already know the synchronous machine is going to work under magnetic locking, right? So it will try to achieve this synchronous speed. Okay, so under the no disturbance condition, omega r is equal to omega s, but under the disturbance condition, omega r is not equal to omega s. Okay, but to run the synchronous generator should need to run means it should need to be equal, right? Okay, so the difference, the angle difference between the rotor axis and synchronously rotating axis, we are going to call it as, this is actually a delta. Okay, and this one we are going to call it as theta. Okay, clear? So exactly the angle difference between the rotor axis and stator axis is not delta, but this is a theta. But angle difference between the rotor axis, we have 10 minutes now. Okay, I will come. Rotor axis and synchronously rotating axis is called as delta, right? So shall I continue? Will be complete. Okay. So now how I can able to write, if I want to write theta, how I can able to write theta as theta is equal to, so theta is equal to delta, right? It is a summation delta plus this omega r into t, that is with respect to time. Okay. So omega r into t. Why I have written, why I have multiplied with the time means, because what is the unit of this theta is the radian. What is the unit of this delta is the radian. I also want this one in terms of a radian, right? If I want to write it, if you want to write this one in terms of a radian means, what is this omega? Radian per second into second, I will get it as a radian, right? You should not add with, you should need to add all with radians only. You should not include only radian per second. So omega r into t will give you radian per second into second as radian. So theta is equal to delta plus omega r into t. Now if you do the differentiation, if you do the differentiation, that is d theta divided by dt, what you're going to give you, d theta divided by dt will give you d delta by dt, d delta divided by dt plus what you're going to get, only omega r. See, this I will show you here. So the same thing, here. See here. So these all are the points which I have covered now. So if you see clearly, so what happened here? See, so d theta by dt, the same thing. D theta by dt is nothing but, so if you are doing the differentiation d theta by dt, you are going to get this one, omega r plus d delta by dt, right? This one is same. So if you do again the differentiation, what you're going to get? You're going to get d square delta by dt square. So what is this one? This one is actually alpha. I have already told this is an acceleration. Acceleration is expressed in terms of angular position of a rotor alpha, which is expressed as d square theta by dt square. Now what is alpha? Alpha is d square theta by dt square is now d square delta by dt square. So just I'm substituting in this equation. If I substitute in this equation, what you will get here, see, PA is equal to, what is alpha now? Alpha is d square delta, sorry, d square delta divided by dt square. So this is actually, we are going to call this as a swing equation. This is actually swing equation. Why it is called it as a swing equation means, actually swing equation, because you are going to observe the change in the angle. I have already told which it should be with respect to d delta by dt. You are going to observe the d delta by d square d delta by dt square perfectly by using this equation. Okay, you can say by using this one, you could be able to find out either the system is achieving the stable or not. You need to do this calculation. But what is PA again? PA is nothing but PS minus PE, right? Because if it is TS minus TE means PA will be equal to PS minus PE. You can observe here, PA is equal to PS minus PE. Therefore, this is actually a swing equation. M d square delta by dt square is equal to accelerating power is equal to shaft power minus electrical power. So this is actually the derivation of a swing. Okay. So okay, if you, now you have, whatever you have a doubts, you can ask. You have completed the derivation of this swing. The chat box is open, you can ask now whatever you have a doubt, because this is a very important question and asked so many number of times. Okay. So I have already told swing equation is only the equation which is with respect to the delta with respect to time. Okay. So one have asked, that is Rajan have asked, what are the criteria for selecting a reference or a slack bus? Okay, so selecting a reference or a slack bus, that is actually not at all related to this concept, but I will say that one. I will give answer to the respective one. Slack bus is, that is the reference bus for every, for example, if this axis has a reference axis, no? Similarly for every power system network there should be a reference bus. Okay, when you are drawing a phasor diagram also, you are going to draw a reference bus, right? Reference phasor. Similarly here also you are going to give a reference bus. That reference bus will have the voltage and delta are the known values, and active power and reactive power are the unknown values. Okay, so and also the very important uh, information or the concept in a slack bus is, it will also give us the information about the losses. What are the different types of loss? What are the losses which it is going to distribute in complete power system network? We can able to find out by using the slack bus itself. Okay, that is the importance of this slack bus. Okay. See, whatever you have doubts, you can ask me related to the any concept, not only this one, related to any concept. Is it okay, Rajan? Is Aftab is there? Saiteja, are you there? You can raise the hand or you can respond in the chat box. Navya, 20 to 17, 20 to Navya, you are coming regularly, very good. And Akila Jyoti, okay. Manasa, Manisha, Moli, Pranay, Vaishnavi. So these 30 members are attending regularly. Okay, we have only 3 minutes left. Manasa or anyone, if you have any doubt, please ask me, because 3 participants raised their hands. Who are those? Okay, right, Monica. Rafiq. Nikhil, I think you are there, right? Nikhil, please send me attendance, because I think today also Aftab is not there. Please send me attendance. Please, I have already told, don't rename with dot 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 like that. Please rename. They have not connected to audio itself. Okay, Sai Nikhil, send me attendance. And so, sir, from third unit, fast decoupled load flow method numerical problem. Okay, I will give you a numerical problem. Okay, I will send you that one. Okay, and I think I have sent you in the Google Classroom about the previous question papers. If you search clearly in the previous question papers, you have the problem related to that fast decoupled method. Okay, just you need to find out. You need to assume some conditions. You need to calculate only the calculation part, that is. Just like Gauss-Seidel or Newton-Raphson, you are not going to calculate any voltage buses like that. That is just a simple calculation. Okay. Manasa, are you understanding? Please raise your hand. And Santosh, Shastri, Vaishnavi, right? Okay, sir, can you explain the Gauss-Seidel Newton-Raphson method again? Okay, I will explain the Gauss-Seidel and Newton-Raphson methods again. Okay. After completion of this stability, okay, this will it will take around uh, 5 or 6 classes. Okay, around 5 to 6 classes, this stability or this 15 unit is going to get complete. Okay, after that one, we will discuss about this, especially methods and also the short circuit analysis. Wherever you have a doubt, with respect to your doubt, we'll discuss in the next class. Okay? Just like if you have told it is a Gauss-Seidel Newton-Raphson, no? We'll discuss after completion this 15 unit again. Okay. Okay. Anyway, uh, thank you all of you. Have a good day.